Okay, Professor Chen, you can start now.
Okay, so yeah. Good afternoon, everyone. So good afternoon, Dr. Pellet. And this is Yao Chen, Deputy Editor of Photonics Research. Thank you for joining Photonics Research Spotlight webinar. So this program was aimed to highlight and showcase research work that was published in Photonics Research. Before I introduce today's speaker, please allow me to briefly introduce you the journal which sponsors this program. Photonics Research is a relatively young journal which was launched in 2013. It has an excellent editor board which works as a gatekeeper, ensuring that only high-quality papers that meet the criteria of journal can be published. All submissions undergo initial editorial review, a process that Lan, Yuri, and I oversee. And the paper passed through this step will go into the standard peer review process, and decisions are made based on comments from the experts in the field. According to the latest journal citation reports, photonics research has received an impact factor of 6.6, ranking number 12 in the category of optics. Although impact factor is not everything, it's still an important reference you might consider when you choose the journal to submit. Here we select some ESI highly cited papers published from 2022 to 2024 to display their citations. You can see the papers in photonics research receive sufficient visibility among peers in the field. Every month, we have one paper selected as on the cover, which is one of the ways to promote research works published in the journal. In addition to that, around 10% of papers can be selected as editor's picks, and one paper can be selected as spotlight on optics each month. So I would like to encourage you to submit your best paper to photonics research. In the submission process, you have the option to upload very nice images as candidates for the on covers, and we do seriously consider those papers. Even if your paper is not selected as on the cover, we will promote your research as recommended articles if you would like to. Photonics Research is co-published journal with the partner OPG, so it has some advantage to enjoy the promotional activities by Chinese Laser Press and OPG. As I mentioned before, we have very outstanding editorial board, which is really strong to the journal development. They consistently strive to promote the journal on different conference and workshops. As you can see, the picture some activities we have done. And the Chinese Letter Press operates its own WeChat platform to serve different purposes. Here are some posts related by CLP. And for example, there are posts about articles in special issues, webinars, interviews with pioneering researchers in the field, and so on. Most of the posts could gain thousands of reading from the general public. From last year, we set a different group called assistant editors. They work with associate editors to go through the papers so that young people could also get experience about the review process. After a few years of experience in this role, they can be promoted as associate editors. Sometimes we invite them to write recommendations for papers we plan to post on WeChat. Here are two examples written by our assistant editors. Every year, we choose 2 or 3 papers as the Editor-in-Chief Choice Award. The standard of choosing them is not based on citations, but on impact and innovations. Awarded papers can come from any group, and everybody has an equal chance, as long as this is breakthrough discovery in the field. So I also want to encourage you to consider that. And in 2021, Photonics Research Webinar was created to give us chance to learn from the experience of pioneer researchers. Some of the stories behind the discoveries offer insights into how to become a significant contributor to the field. We have interviewed Professor Malan Scully in 2021, Professor John Boyce in 2022, and Connie Chen in 2023. Photonics Research also organized workshops. We choose one interesting topic to share with the community. Through these workshops, we have opportunities to have in-person meetings with potential readers and authors. The topics have included optical micro cavities in 2019, and silicon photonics in 2020, deep learning in photonics in 2021, and integrated photonics in 2022. And last year is about optical matter surface. It's last year, August. In order to enrich the format of promotion and allow more people to learn about our authors' research work, we have launched an online presentation called Photonics Research Spotlight. So far, we have held 5 sessions with an average of 1,000 audience. After online talks, the recording of presentation will be distributed via email campaign. And to establish a journal with greater reputation requires contributions from the community. For example, last year we celebrated Photonics Research 10 years anniversary with events featuring talks shared by authors and panels show top tier researchers. We believe that this kind of discussion is really helpful to the community, especially young researchers. The first venue was in Tsinghua University and followed by the University of Science and Technology of China and Zhongshan University. There were just a few examples to show strong support we have got from the communities. And our editorial board members come from all over the world, and we hold online editorial board meeting regularly to discuss discuss how to make the journal better. Last year, coinciding with the journal's 10 years anniversary, we had an offline editorial board meeting. And in addition, our editors also participate in varieties of events actively to promote our journal. We also organize features issues every year, similar to the way we choose the topic for the workshops. We solicit the feedback from the community. For each issue, we have multiple guest editors who already have established their reputation on that topic. This year's issue focused on advancing integrated photonics. We are now collecting feedbacks from next year's issue and welcome the suggestion from all of you. And if you have any questions, suggestions to improve the journal, welcome to contact us. And now, I think it's my great pleasure to introduce today's speaker, Dr. Maximilien Bellet. He is an R&D project coordinator in the field of integrated photonics, mainly on lasers, modulators, and nonlinear materials, heterogeneous integration. Currently, his main focus is the establishing EU materials scalability via heterogeneous integration on CMOS platform. The article will be shared today is heterogeneous tunable III-V-on-silicon-nitride mode-locked laser emitting wide optical spectra, which was chosen as spotlight on optics. Now let's welcome Dr. Maximilien Bellet to share more insight about III-V-on-silicon-nitride mode-locked laser. And Dr. Bellet, it's your time. I will stop the sharing.
Okay, thank you very much, first of all, for the invitation, for the paper, and also for the online presentation, and also for that very nice introduction of the journal, and also from myself. So I will start to share my screen now. Okay, can you see my screen? That's fine?
Yes.
Okay, perfect. So then I'm gonna start. So I will not present myself anymore since you already did it very well. So thank you again for that. So yeah, today I will discuss III-V-on-silicon-nitride mode-locked laser and show how we reach a stable mode-locked laser where we can also tune the optical comb that we can generate. So this work has been done at Ghent University and also imec, because I have both affiliation, and in the team of Professor Bart Kuiken. So this is a bit the overview of the talk I'm gonna have today. So first, I will give a brief introduction on the status of active silicon nitride integrated photonics, and discuss a bit how heterogeneous integration can provide new functionalities on mature platform. And I will also show a brief state of the art and highlight some results we obtained at Ghent University. Then, of course, I will focus on the results selected as a spotlight today, consisting in a stable III-V silicon nitride tunable modular laser. So I will discuss the fabrication up to the characterization of that laser. And then I will discuss that results and try to include the results in a wider context to also provide some perspective and see what are, from my point of view, the next milestone to reach, and what could be interesting, in my opinion, to do to prove the reliability of our approach, which is mainly consisting in heterogeneous integration. So the first thing I would like to introduce is a bit something very well known in the integrated photonics community. This is the silicon and the silicon nitride platform. So both of that platform are CMOS compatible. So because of that, they are considered low cost and scalable, and also very mature. So the thing is, there is still some difference between silicon nitride and silicon, because that's two different material. And in our case, we at least for that work, we made the choice to work on silicon nitride for several reasons. So the first one is the transparency window, which is pretty wide. So from 250 nanometer up to around 5 micron. Then the propagation loss of that material can be also very low, so typically below 1 dB per meter. The 2-photon absorption is also negligible, at least for telecom wavelengths. And the industrial status, as I said, it's a CMOS compatible technology. So then up to now, of course, it's less consequent than electronic technology, but for photonics, we can consider that to be middle volume production. And also the level of the industrial status is, let's say, R&D. But that material still lacks some properties. So, for example, you cannot have optical gain intrinsically. Also, there is no real possibility for fast modulation because there is no intrinsic Pocal effect. For the nonlinear conversion, it's a very efficient material for Chi3 nonlinearities, but there is no intrinsic Chi2. And for the detection, similarly to the optical gains, there is no direct detection in that platform. But still, that platform is very efficient, and it's a very good platform to work with because it's very mature and already some process design kit of passive components, very strong passive components reliability are available. And for that, you can obtain all the passive devices you need, like IQ ring resonator or directional coupler, grating coupler, mirror, and so on. And then it allows us to design very efficiently on that platform. But if we discuss about integrated photonics up to now, let's say the view that we could have in a real application would be to have the silicon nitride chip, but this is not enough to have the passive circuitry. And of course, if you want to build the system, you also need light source, photodetector, and depending of the considered application, you can, for example, modulate the light. You also probably need to convert the wavelengths and things like that. So up to now, we have the chip to conduct the light, but everything around is not directly integrated on the chip. So it's really difficult to say that now it's really an integrated system, because the circuitry is integrated, but everything around is not really on the chip, and it's more like bulk devices. But for that, in the past years, so many researchers works in the direction to integrate that active functionalities directly on the chip, and several methods exist for that. So here I will summarize 3 of them. So the first one is the flip chip integration, where you can fabricate the device, dice them, and they pick and place on your wafer. Another one is the wafer bonding technology. So in that case, it's a bit different because you directly bond the material you want on a host wafer, but then you still need to process your device. And another approach is, for example, the photonic wire bonding, where you can put your active devices on an external chip, and then link that active functionalities through very thin wire in order to conduct the light from the active chips to the passive chips. So the integration techniques existing are not only mentioned there. There is also other techniques, and it's a very vast area of research, but it's also pretty active. So now many people try to improve that. And this is, in fact, what we do at Ghent University imec. And in our case, the approach we choose is called micro transfer printing. And why we choose that approach is because we really think that it's the main advantage is that it's a versatile solution. So in that case, the idea is to pre-process the devices on what we call a source wafer. So then we can process the active devices. And then we encapsulated that device in an encapsulation. And also we have some mechanical structure that we call tethers. And then we can release under edge that devices to leave it suspended. After that, using a PDMS polymer stamp, we can pick that device and print on the wafer. And then we can remove the encapsulation and populate the active functionalities we want on silicon or silicon nitride wafer. So the micro transfer printing shows very high integration density because you can fabricate a lot of devices on a small wafer and populate the host wafer a bit everywhere you want. It's backend compatible, so it means that you can keep the CMOS compatibility for the silicon and silicon nitride platform and process your active device in an external fab. You really highly efficiently use the material because it's really a dense array of devices. So the alignment of that technique is pretty low. It's below 1 micron. And it shows also, as I say, as the first point of that slide, high versatility because you can also mix the different device and populate on the same CMOS platform. And it's, let's say, low cost and start to be R&D maturity level. So then if you use that technique, you can take the same schematic as I presented 2 slides before that. And you can imagine that now you have that CMOS platform. So in our case, again, it's a silicon nitride. And then instead of having bulk devices around to include some functionalities, active functionalities, you can directly print the functionalities you need on the silicon nitride chip or wafer. So for example, you can imagine to have a system including, again, your light source, some modulator, some wavelengths or frequency converter, and also some photodetectors. So now I will highlight some results we obtained using that micro transfer printing technique to show a bit that we can do a very interesting demonstrator using that approach. So the first one is the fabrication of an heterogeneous laser on a thin film lithium niobate platform. So the idea is to pre-process the laser in a 3-5 wafer. So for that, we process a 3-5 material gain that we can do in advance. And in fact, we have the gain, so as you can see there, but we also have the cavity of the laser made with a bright grating in silicon, and we can directly transfer print all of that device in the thin film lithium niobate platform, as you can see that. So that platform is provided by the team of Marco Lonca. And then we can transfer print that device, so which is a tunable laser. And then the laser can directly operate on the thin film lithium niobate platform. So this is what we have done. And to demonstrate the co-integration of that laser with the thin film lithium niobate, in fact, we pump an electro-optic ring resonator. So that laser allows us to generate a frequency combs by having cascaded electro-optic modulation of the middle line and generate successive line in our comb. So this was a first demonstration. Another one to show also a bit the versatility of the micro transfer printing technique is the demonstration of the transfer printing of lithium niobate. So lithium niobate is let's say a popular material in the past 5-6 years because it shows very huge electro-optic coefficient. And because of that, you can have high-speed modulator. So here we also show that, for example, we can transfer print directly lithium niobate on a silicon nitride circuit. So as I mentioned at the beginning of the talk, silicon nitride doesn't have electro-optic effects, so it's difficult to have high-speed modulator. But then you can fabricate, for example, a device consisting in the Mach-Zehnder modulator, where you add the lithium niobate using the micro transfer printing, and then obtain electro-optic modulator directly on silicon nitride. So we have done that and shows that the concept is working, and also obtain some data transmission results. And also now we are also even pushing that technique to have a longer device to transfer print to decrease the VPI and then to increase the efficiency of the modulator. And we demonstrate that we can transfer print up to 1 centimeter long devices. And also here you have a nice view of the source used to fabricate the coupon. So it really shows the density of the device on the source sample, because you can really see that many coupons can be very close together, and then you can pick them and spread them everywhere you want on a host substrate. So yes, we demonstrated a high-speed modulator with a pretty low VPI, and now we can also transfer print very long devices. To show that also that techniques allows for more exotic integration, let's say, we also work with less popular materials. So one of them is gallium phosphide. So gallium phosphide is a 3-5 material with a wide band gap. And it also shows very high nonlinearities, both for Ki2 and Ki3. And then we demonstrated using that micro transfer printing that we can transfer print very wide membrane of gallium phosphide. So in that case, it was a membrane of 500 micron by 500 micron. And then we patterned some very long waveguide on that gallium phosphide platform. And by pumping it with a mod-lock laser, we show that we can obtain a super continuum based on the Ki3 of the gallium phosphide. Another result, maybe project I will discuss a bit, is that, okay, of course, at the beginning, I say that now the idea would be to have a system where you can use a silicon nitride CMOS circuitry. And using that micro transfer printing, we can populate the wafer to place some active functionality on the wafer. These are still work in progress, but we already have some projects like that. And this is one of them, so called Vision. It's owned by the Horizon Europe agency. And here the idea is to work at wavelengths below 1 micron. So we use the silicon nitride transparency properties to guide the light at that wavelength. And then we try to obtain all the active devices operating at that wavelength and populate that wafer using the microtransfer printing. And here it will be a real demonstration of the fact that we can really build a full system using the microtransfer printing. So for that, we are developing a gallium arsenide laser where we can have a lasing up to around the 900 nanometer. Also that lithium niobate modulator and also the photodetector. And in that case, it will be a silicon photodetector. And all of that 3 device could be transfer printed on the silicon nitride target. So yes, so I think with all of that examples, I introduce a bit the heterogeneous integrated photonics based on the use of the silicon and silicon nitride mature CMOS technology, and also how we do the heterogeneous integration at UGent using the microtransfer printing technique. But now I will focus more in detail on the, let's say, the heart of that talk, which is that III-V silicon nitride tunable modular laser, and in fact, which is one extra example on how microtransfer printing can allows us to fabricate active devices on silicon nitride. So before that, I will very quickly introduce again what is an optical frequency comb, because in fact, the modular laser is a source of optical frequency combs. And in optics, a frequency comb is a source whose the spectrum consists of series of discrete and equally spaced frequency line. So you can see on that schematic that you have really a lot of optical line equally spaced together. But in fact, there is a few parameters to take into account where we discuss about optical frequency combs, the bandwidth of the combs, the repetition rate, which is the distance between two subsequent optical line, and also the frequency offset, which is the frequency of the first optical line. So the repetition rate, the space between two lines, is very easy to measure, but the frequency offset is more tricky, because if you want to measure that frequency offset to characterize fully your frequency combs, you need to use nonlinear optics to double the one of the line, and this means that you need a pretty high power or pretty efficient Chi2 nonlinearity. And also you need a very wide comb, because it needs to be octave scanning to make the pitching between two different lines, and from that obtain the frequency offset. And that referencing of the comb line, then yeah, it's really pretty tricky to do, even if it's still possible. But then mainly for integrated modular laser, the level of power plus the fact that the comb is not octave spanning make it very difficult. So with frequency combs, you can really reach many applications. So based on a frequency comb and modular laser, yeah, modular laser is a source of optical frequency combs. And if you assume that you can have a self-reference comb, so meaning that you know the frequency offset and the repetition frequency, you can really reach many applications. So typically you can have high precision optical frequency measurements in the field of, for example, optical clock. You can also work in the generation of microwave by using the beating of several lines. You can also do some astrocomb to use your comb to detect some line coming from the optical line coming from space. And also, of course, like another example is, for example, the spectroscopy. But all of that application are based on the fact that you fully reference your comb. So you know the frequency offset and the repetition rate. And as I already said, it is very difficult to do that with an integrated modular laser because the power that you can provide and the width of your optical spectrum are too low. So it's really tricky to reference your comb. But still, you can use integrated modular laser to generate frequency combs. And instead to work with self-referenced frequency comb, you can still work with dual comb. So here the idea is to generate two optical frequency combs coming from two different modular laser and make a beating between the two combs. And when you do that, in fact, you can avoid the use of the self-referencing and still you can obtain some application using your comb, even if you don't know directly the frequency offset. And it is several people work on that field. And it allows, for example, to do some dual comb spectroscopy or dual comb ranging. Also, recently, some team shows that you can generate a terahertz wave using that technique. And as a nice picture from NEST, in fact, it's really like a direct link to the RF domain, because when you make the beating between the successive optical line, the frequency that you obtain at the end is in the RF domain. So then you can keep the high precision of the optical measurements and convert that in the radio frequency domain and measure the signal with very low cost electronics, but still keeping the quality of an optical measurement. So now I will show a bit more in detail how we fabricate a modular laser on silicon nitride using heterogeneous integration. So in fact, it's a bit, let's say, an historic diagram on how people fabricate integrated modular laser. So as I mentioned very early in the presentation, silicon nitride, you don't have gain in that material. So in the past, what people did was to directly use III-V material, so typically indium phosphide, and fabricate integrated laser and modular laser in that platform. So for that, they take indium phosphide wafer and they etch a waveguide, add some metallization. So of course, in that epitaxy, you have a quantum well to provide gain. And then based on that, you can directly pump your waveguide electrically and obtain gain. And using that technique, you can have a laser. So directly fabricating the laser in a III-V platform. But in that case, the cavity is pretty small, so meaning that the quality of your optical line generated by your laser is not very great. But then what people start to do is to work with extended cavity laser. So for that, they separate in the architecture of the laser the path of the light where you have the cavity, which is a passive cavity, and also the part of the device where you have gain. So it is also has been demonstrated in an indium phosphide platform. So it's more or less the same as the first example, but the only difference is you don't have gain everywhere in your cavity. And because of that, you can have a longer cavity, longer optical path, and meaning that you can increase the noise property of your optical signal. But that has been demonstrated in a III-V platform, but still a III-V platform, the loss of the platform are still pretty high because the refractive index of the III-V is pretty high. So it's very sensitive to the sidewall roughness of your waveguide. And then it means that you still cannot reach very high quality laser. So then using heterogeneous integration, you can use the best of the properties for two different platforms. So for the passive circuitry, for example, you can use silicon or silicon nitride. And this is a very low loss platform. So typically for silicon nitride below 1 dB per meter. So then it means that you can have a very high quality resonator to make your laser cavity. And then you can heterogeneously integrate the gain on that platform. So like that, you can still have a platform with gain, but based on a low loss propagation platform. And if you do that, you can finally obtain a laser where you have the III-V gain, but on a low loss laser cavity, and increase the quality of your lasing line. Of course, now I'm discussing a mod-lock laser, which is not simply a CW laser. And the difference is in all of that example, you also need a component to make the mod locking of your laser. And in that case, it's called a saturable absorber. So that saturable absorber is directly made in the gain section. And that saturable absorber allow you to convert, not to convert, but to shift from a CW laser into a mod-lock laser and then generate optical frequency comb. So to fabricate such a laser, so one of the popular technique is the heterogeneous integration, of course, but how to do that heterogeneous integration? So one very popular technique was the wafer bonding. So many John Bowers is working a lot of that and has a lot of very nice results. But this is a view of how the wafer bonding could be used to implement some III-V on the silicon platform. And as you can directly see, the size of the III-V wafer doesn't match the size of the CMOS 300 or 200 millimeter wafer. And then the integration density is not optimized because you always leave some blank space on your wafer where you don't have the III-V active devices. So that platform based on the SOI with wafer bonding of III-V wafer is already let's say mature process, and with that technique you can have a very efficient laser. But it's still a bit difficult to integrate your III-V very efficiently everywhere on your wafer, because you have some kind of a partial covering of the platform. But still, that techniques works very well, and efficient tunable laser and mod-lock laser are demonstrated, and it's already at least in the field of heterogeneous integration, maybe one of the most mature technology. So then we do something pretty similar, but instead of using the wafer bonding technique, we use the micro transfer printing technique. And then again, the silicon nitride platform allows us to have a very suitable circuitry, so low loss and based on the use of a process design kit to fabricate the laser cavity. And the integration of the III-V gain is then done by heterogeneous integration via the micro transfer printing technique. So just to maybe re-explain a bit, because it's not something very familiar for the people. So we have that III-V material gain, and we encapsulate that III-V in a structure. Then we can under-etch the device, and then we have some mechanical support leaving the device suspended that we can break while picking the device with a stamp and transfer on the silicon nitride wafer and populate the silicon nitride wafer with the gain. So here, I'm not sure it works, but anyway. So here you have a view of, for example, coupons that we can pick and transfer print on a waveguide. So now I will describe a bit more in detail the architecture of our laser. So as every laser, so this is made with a laser cavity. The laser cavity is made in a silicon nitride material. So the circuitry there is a silicon nitride low-loss waveguide. So you also have spirals to increase the length of your cavity in a very low footprint. And then we also have some mirror, because to make a laser cavity, you need some mirror. And for that, we use a Sagnac mirror. So it is simply a loop with a directional coupler. And we have two of them. So one is almost 100% reflective, and the second one is a semi-transparent mirror where you can also leave some light passing through that mirror. And in the middle of that, of course, we have the gain. So the platform is really a regular silicon nitride platform on insulator and on silicon substrate. So this is done in a CMOS fab at imec. And then when we have that circuitry, we can populate the circuit with the gain. And at the end, we obtain something like that. So the stack is pretty complicated, but in fact, it's not so complicated. So you simply have the CMOS silicon nitride circuit. And then on top of that, we have a regular semiconductor optical amplifier, which is consisting in a diode, including a multiple quantum well to provide the gain, encapsulated in a N and a P contact. And we also have an extra layer of amorphous silicon, but this I will come back to that. So yes, so in fact, we can with microtransfer printing provide some gain on top of silicon nitride platform. But there is still also the question of the coupling of the light, because the light is in the silicon nitride waveguide. But then, if you want gain, you also need the light to reach the III-V amplifier. And for that, we use a adiabatic coupling technique. So the idea is we have the light propagating in the silicon nitride, and then using a set of taper, you can push the light on top of the silicon nitride and push that light in the III-V. But for the silicon nitride material, the refractive index is very low compared to the III-V material. Then it's very difficult to directly push the light from silicon nitride to the III-V. And because of that, we need an intermediate layer, and that layer is amorphous silicon. So like that, we can do like a two-step transfer of the light from the silicon nitride to the III-V. So first we go from silicon nitride to amorphous silicon, and then from amorphous silicon to the III-V. So here you have the cross-section showing the optical mode profile in the platform. So at the beginning, the light is in the silicon nitride. Then we smoothly taper an amorphous silicon waveguide on top of that. And then the light went from the silicon nitride to the amorphous silicon. And then as a last, we do something very similar and do an extra taper from amorphous silicon to the III-V. And we finish with what we want originally, with some light seeing the multiple quantum well of the gain device, making possible to amplify the light on the silicon nitride circuitry. So those are some close microscope picture of the device. So one very important part of the device then is that taper, because as I explained there, that taper in the III-V is very important to couple the light. And if you want to make it efficient, in fact, you see that it needs to be very narrow, so typically around 500 nanometer. So then here are some view of the taper after etching. So the etching is done with a combination of dry and wet etching, and we can fabricate a very narrow taper. Also, an important thing to mention is that amplifiers are pretty thick. It's more than 2 microns. So the aspect ratio is pretty high because you have a very narrow 500 nanometer taper over a full stack of more than 2 microns. So it's still something that you need to take into account when you do such a design. So these are more view of the taper, but after a wet etching. So you can see that at the end you can really finish with a very narrow taper. And then another very important step in the fabrication of the gain is also really the active region of the semiconductor optical amplifier is the quantum well. So after we pattern the taper, we also need to pattern the quantum well. And here you can see the quantum well, which is pretty thin in fact, but you can see around the quantum well. Also here you can see it very well. And this is really where we can obtain the gain when we pump the PN structure. So that gain is made with 2 different regions. So the first one is the gain section. So the gain section helps to amplify the light on the silicon nitride. But again, because we want to fabricate a modular laser, we also need a saturable absorber. And for that, it's in fact pretty easy. So the only things that we need to do is to electrically isolate the gain from the saturable absorber. And for that, we can etch 2 small trench around the saturable absorber to electrically isolate the saturable absorber section from the gain section. So here you have 2 cross sections showing the gain. So the gain, you really have the full structure, the P and N contact and the multiple quantum well. And in that small trench, in order to electrically isolate the gain section and the saturable absorber section, we etch the P layer of the indium phosphide. So here we etch the P layer. So then it means that the current cannot flow from there to there because you have an electrical isolation. And because of that, you can electrically drive the gain section separately from the saturable absorption. And using a reverse voltage, you can have 2 different operations, amplify the light or a saturable absorption of the light. So now I will show a bit more in a laser architecture level how the device looks like. So since the beginning, I'm discussing the microtransfer printing and the fabrication of the suspended devices. So this is now how they looks like for gain. So indium phosphide based gain for a laser. So here you have 3 different coupons of gain, and you can also see the narrow taper to couple the light. And all of that 3 gain devices are suspended, and you can see they are still attached to the host substrate with that mechanical structure called tethers. And in fact, you can also see that this is suspended because here you have some kind of color coming from stress in the encapsulation material, meaning that the device is really suspended. So then this is from the III-V gain. And also we have the silicon nitride circuitry. So I described that a bit already. So we have the silicon nitride waveguide, the low-loss waveguide, the 2 mirrors to fabricate the laser cavity. And here you have the place, the location where you want to add the gain. Also including the amorphous silicon taper structure to make sure that we can couple the light. And this is before the heterogeneous integration via transfer printing, and then this is after the transfer printing. So it's exactly the same circuit, but then we place the gain on top of the laser cavity. And as a final step, we also do a last metallization in order to provide the metal contact to the gain and make sure that we can probe the gain device. So in between that, I will also again shows a bit that microtransfer printing is from our point of view a very nice technology, because it really allows to have a very high density integration. So, for example, this is the size of a 2-inch III-V wafer, and you can see on such a wafer we can really have many devices of gain very close together. So in fact, it's more than 4,000 devices in a 2-inch wafer. And then this is like a preliminary step into the scalability of that technology, because you can spread all of that gain devices on a silicon or silicon nitride CMOS wafer. Also, up to now, some wafer scale printer allowing to print on 200 and 300 millimeter wafer are commercially available. So we can really imagine to scale that technique using microtransfer printing. So after we fabricate the laser, then we still need to measure the laser. And for that, this is using a pretty simple setup. So on the setup, we have the laser chip. Then, of course, you have an optical fiber to collect the light generated by the laser. And also we have an electrical probes to provide the current to the gain. And in fact, that probe, it's linked to 2 different electrical source, one for the gain, where we want to apply positive voltage, and one for the satural absorber, where we want a negative voltage in order to make sure that the laser can mod lock. So this is to drive the laser. And then when the laser is electrically driven, then it starts to generate the light that is collected in the fiber. And the light is then converted with a fast photodiode into the radio frequency domain, and it allows us to see the electrical spectrum, and then it allows us to see the laser line. So here it's an example where the laser operates in a CW, and also on top of that we also collect a part of the light in a power meter to measure the optical power, and in an optical spectrum analyzer to see the spectrum of the laser. So this is a typical result that we can obtain using that setup. So here, what you can see, in fact, it's directly the optical frequency comb generated by the mod-lock laser, but not in the optical domain, but in the radio frequency domain. So after the conversion with the fast photodiode, because that line are so close together, so the repetition rate of the laser is 3 GHz. So the line are so close together that we cannot directly measure the comb in an optical spectrum analyzer, at least with the optical spectrum analyzer we have at universities. It's the resolution is not good enough. So then we convert the optical comb in the radio frequency domain, and we can still measure the comb line. And as I said really at the beginning of the talk, it's really easy then to measure the repetition rate, because it's simply the space between 2 successive lines. And you can even zoom on one line as we do there. And then you can also again measure the repetition rate and see the quality of your RF line. So there is also 2 ways to drive your laser for the saturable absorber. In fact, for the satural absorber, you can just drive it with a DC voltage, a negative DC voltage. But you can also improve the quality of your laser by driving the satural absorber at the same frequency of the repetition rate of your laser. So in that case, for example, the natural repetition rate of the laser defined by the cavity length of the laser is 3 GHz. So if you drive the satural absorber with an RF external signal of 3 GHz, in fact, you can see that the mod locking is a bit better, and the bandwidth of your radio frequency signal significantly decrease. And the last measurements then is the optical spectrum. So here you have an example of an optical spectrum. And here that one is around 15, 17 nanometer. So here you can see the envelope of the comb, but of course, as I said, you cannot see the laser line, but in fact, that laser line converted in the RF domain normally are really included in the spectrum, but we cannot resolve that line directly with the optical spectrum analyzer. So one of the first step was to set to tune the laser lasing wavelengths, because we are interested of laser lasing around the 15 nanometer, the telecom wavelengths, and how to choose the lasing wavelengths. So first of all, of course, by choosing correctly the laser cavity in silicon nitride parameter, but also the gain, the ASC of the gain is to be chosen to have a gain at the correct wavelengths. And for that, you can tune the multi-quantum well parameter. And this is what we did. So we fabricate several gain with several multi-quantum well parameter that are described with the photoluminescence wavelengths. And we can match what photoluminescence wavelengths allow us to get lasing at 15 nanometer. So in that case, that gain, that stack of multi-quantum well can allow us to lase around the 15 nanometer wavelengths. So the telecom wavelengths where all the cheap optical components are commercially available. So then that graph is a bit more complicated. So in fact, the modular laser we fabricated is pretty stable, and it doesn't allow us to only generate one optical frequency combs, but a lot of flavors of optical frequency comb. So in the laser, the only parameter we can experimentally tune are the gain section, let's say the amplifier section. So then you have the gain that you can drive and also the saturable absorber. But the thing is, depending on how you will drive your gain and how you will drive your saturable absorber, you can have different flavor of mode locking and lasing. So that map really summarizes all of that results. So when you tune the gain and the saturable absorber, you can obtain really all of that flavors of mode locking. And what is the first things to take into account is we have some different regime of mode locking. So for some of them, the mode locking is the fundamental mode locking, where we have it's that one. So we have the fundamental mode locking for all of that region. So for example, for that gain and that value of saturable absorber, you can have such a comb, the same there and extra. And here you really have the 3 GHz repetition rate. So meaning that the mode locking is reached at the fundamental value of the cavity. But then if you also shift more the saturable absorber value and the gain value, you can have another operation of your laser where you still have mode locking. But you can see in that case, the repetition rate become different. So in fact, you can really choose what you want based on that map. And you can see that the region of stability are really wide. And then you can really choose depending what you need, the parameter you want to use to provide your laser. And also the thing is, if you are interested by the mode locking, the fundamental mode locking with the repetition rate corresponding to the repetition rate of your cavity. So in that example, 3 GHz, depending how you will drive your laser. So you have all that purple area that works. So for all that set of parameter. But then if you play with the parameter inside that purple area, you can still play with your laser properties. And in that case, this is what we have done for that. And then you can tune the wavelengths of the laser. So in that case, all of that points are coming from that area. So where you have 3 GHz mode locking. but then we can shift the optical spectrum of your laser. So all of that spectra are shift every, let's say the center of the spectra is shift every 10 nanometer. But all of that signal are corresponding to an optical frequency comb. So of course, here you cannot see the optical frequency combs line because with the optical spectrum analyzer, we cannot resolve it. But inside all of that spectra, you have really a lot of optical lines that are coherent and modlocked together. So here it's just a view on how you can tune the wavelengths by changing the gain current. So a last thing to do is also to optimize the stability of the cone. And for that, it's mainly based on how you want to push your light in the multiple quantum well. So for that, we did like a Monte Carlo study by taking every parameter of the laser into account to find what is the most stable. And when we do that, we can reach very wide optical spectra while the laser is still mode locking. And here you can see that we can really increase the width of the optical combs generated by playing well with that parameter. But it's a bit a trade-off because in fact, to have a laser, you want a lot of gain to make sure that the laser can laser. So for that, you need confinement in the multi-quantum well. So you want the light to be strongly there to amplify it very well. So then you can have very easily a laser. For the saturable absorber, that's the same. If you want the saturable absorption effect, you want the light to be in the III-V material. So then this is fine. But the thing is, for optical semiconductor amplifier, if you have too much light in the amplifier, there is also saturation effect. And then if you do that, you will lose some power. So it's a bit a trade-off because for some of the characteristic of the laser, you want the light really in the III-V, but for some, you want the light not too much in the III-V, otherwise the gain will saturate. And then that's why by playing a bit with the quantum well, multi-quantum well confinement, you can obtain different results. And if you optimize that, then you can have a very wide optical spectrum. So this is another things that we did is also the packaging of that laser. So here you can recognize the laser chip. And in fact, instead of driving the laser with probe, we wire bond that laser on a commercial PCB. So this is done by the company called Fix in Netherlands. And also they can put some electrical connectors. And here you also have a fiber array bonding at the output of the laser. And then that laser can operate, but directly in that small module where you can drive the gain, the saturable absorber, and collect the gain, sorry, both of them, the saturable absorber, and collect your light. So I think that was mainly the presentation of the Modlock laser results. And now I will try to put a bit that results into a perspective to explain from my opinion what could be the next step and how we could work in the direction to make more demonstrators to prove the reliability of that micro transfer printing approach to fabricate active devices. So very quickly, well, probably all of you already knows, but the quantity of data used in the past year and always drastically increase every year. And all of that data are managed by a data center. So the data center is like a big block, making sure that you can deal with all of that data. And that data, in fact, you need to collect them and transfer the data from data center to data center, or also in a data center, there is a lot of exchange in data. And in fact, so photonics, with photonics, you can improve that that technology, because if you can transmit data using light, in fact, you could decrease the power consumption of all of that system. And for that, you will need very stable light source. And all of that technology, for example, use what we call wavelength division multiplexing. So you can transmit data on different wavelengths to increase the data rate. So because it's like a parallel operation. But then I will not go into the detail, but you have different kind of multiplexing and extra. But then the message of that is, if you have multiplexing plus a light source and high-speed modulator, then you can use the photonics technology to deal with datacom, and this could be very interesting. For example, to use such integrated devices in such systems. So for integrated photonics, in fact, so one of the interesting platform is the thin film lithium niobate, because in data center, you need to modulate the light. So you need the modulator to transmit the data. So the thin film lithium niobate platform does that very well with the huge electro-optic effect. And then you also need a multiplexer, so to split your light into different channels. And this is something that is already possible. And in fact, some companies, as Hyperlight, which is the company led by Marc Olonca, they already commercially offer such a solution where on a chip you can have a multiplexer and also a high-speed modulator. But if you have a look on such a chip, you have the multiplexer and the modulator, but you still don't have the light source, so the laser. And this is still a bit the bottleneck. If you want more integration directly on a chip and increase the complexity of your system, you also need the light source. For example, at imec, we are doing, let's say, similar things, so but not on thin film lithium niobate, because thin film lithium niobate, it's a very efficient platform, but the maturity of that platform is a bit lower compared to CMOS platform as silicon or silicon nitride. But at imec, we have that silicon platform called IC200, and it's based on what we call a module. So the module are all the things that we can use on that platform. And that module, we also have like wavelengths division multiplexer. We can also already have some modulation and also germanium photodetector. So everything included on that platform. But again, it's still lacking from the light source. And also the modulator up to now are fast, but not fast enough for the next generation of integrated photonics. And then, so still lacking for light source and also for high-speed photodetector, like the electro-optic, not photodetector, modulator, like the electro-optic modulator. But then, with the heterogeneous integration, we can imagine to add the electro-optic modulator and the light source directly on such a platform. And this is a bit where the integrated transfer printed heterogeneous laser could play a role. So, for example, we have I discussed today that modular laser, and it's a very good candidate for telecom and datacom, because in fact, you can imagine that each of the laser line could drive one of the multiplexer channel, be modulated, and then you can transmit data like that. But we also have another solution with the transfer printing heterogeneous integration, which is to fabricate tunable laser. So two of that example could, for example, be a very good candidate to drive such platform. So on silicon nitride, or even on thin film lithium niobate, and be placed in data center or a telecom system. So I think I will now start to conclude. So then, well, I think what I tried to say today was that the CMOS platform in general, but here mainly the silicon nitride platform, is very efficient for passive circuitry because it's mature and it's really comfortable to work with. And then the heterogeneous integration allow to unlock some active functionalities. So mainly today we discussed the gain to make sure that we can fabricate laser. And for that, we use micro transfer printing because it's a versatile technique. So here we focus on the integration of gain on the silicon nitride platform to demonstrate a modular laser. And that modular laser using the III-V gain and structural absorber is pretty stable. So it's even a tunable modular laser because by playing with the gain and structural absorber parameter, we can tune the optical spectra generated by the modular laser. And also the co-integration of that modular laser with other material is now possible because of the versatility of the micro-transfer printing. So then with that, you can also imagine now to fabricate more some system. So then I think now, as I start to discuss a bit at the end of the talk, so now I think the demonstration of system using that integrated modular laser on silicon or silicon nitride would be very interesting. So for that, it could be a system based on dual count spectroscopy, where you use two of that modular laser together to make a binting between them and do some and build some spectroscopy system. But you could also do some dual comb ranging to measure some distance variation. And also, I think one of the very good candidate of system that would be interesting to demonstrate would be to include that such a laser in a datacom system, as I really explained at the end, but combined with really high-spin modulator that could be also co-integrate with that modular laser, so typically electro-optic modulator. And I think the second point is also to work in the direction of that co-integration. So for example, laser and modulator, and also the scalability of that technology using micro-transfer printing. So as a small last remark before to conclude the talk, I will say that, yeah, now there is really a vast set of possibilities using that heterogeneous integration and micro-transfer printing, which is very interesting for research and innovation. But also now, everyone use different technique, different architecture, different design, different materials. So a bit of homogeneity in all of that approach would also help. If we really want the integrated photonics to increase its impact in industrial ecosystem and society, because it will really help people to use that technology a bit like what we have in CMOS technology. It's more or less standard. We have some process design kit and things like that. And then even if people are not an expert in that field, they can still design and get their chip and make them working. And this is a bit, I think, the next step to move from the academic research to R&D for real life application. And this is now what I'm really trying to do with imec and UGent, and we try to push that system in real life. So then I will conclude. So thank you very much for your attention. And I would really thanks to everyone from the team of Professor Bart Keuken and all the people strongly contributing to that result. Thank you very much.
Okay, thank you, Dr. Alex, for the excellent talk. And I have two questions from the audience. So first one is, what is the alignment precision of the micro-transfer plating? What factors are critical to alignment in your case?
Yes, so but mainly it's a question that we always have. So mainly the alignment is critical for the coupling from the silicon nitride to the III-V. So the taper needs to be precisely aligned on the amorphous silicon. Otherwise, you cannot reach that coupling. But that's why, in fact, we use that adiabatic coupling, because using that technology of taper, in fact, we have more than 99% coupling up to even 1 micron misalignment.
Mm-hmm.
And in fact, that's exactly the possibilities of microtransfer printing, which is 1 micron. So in that talk, the transfer printer I used was 1 micron accuracy, but now we have also commercial tools that are available. I show one, I think, at some point. Yeah, okay. So such a tool, it's even lower, so you can reach like 500 nanometers 3 sigma misalignment.
Okay. And so what will be the unique advantage of micro transfer printing over wafer level thin film bonding?
But I think, so clearly, okay, so that picture speaks very well, because, so like, let's say another approach is the wafer bonding, and it works very well and is very mature. But you can see, if you imagine to co-integrate different material with a wafer bonding, so first you have, for example, the III-V, then you need to process your device. Then if you want a modulator, you need to bond modulator and process your device. And then if you want a detector, you need to bond the material for the detector and process the device. While with transfer printing, I think the main advantage is the versatility, making possible the co-integration. So you can prepare separately all the device you want, and you can populate your wafer with different functionalities. And then you can even reuse that source of wafer to populate another wafer. So maybe, yeah. So for example, you see that sample, it's a sample of lithium niobate coupons that we can use. So you can populate a modulator and then say, okay, 2 days later, you can say, I will use the same coupons and populate, I don't know, another chip or another wafer or something like that. So the versatility for me is the main advantage. But there is also, let's say, the disadvantage is compared to the, sorry, I'm looking a bit for the slide. So comparing to that technique again, they already demonstrate the scalability with wafer bonding. For microtransfer printing, it's a work in progress, but lot of nice advances are done in the last years. But now, yes, it's the versatility of the technique, but combined to the scalability is really important too. And this is work in progress, the scalability, but I think it will be possible.
Okay, so I think it's time to close, and thank you for this great talk, and thank you for choosing photonics research. I think today our spotlight is we can finish it here.
Okay, I'm just trying to unshare my screen, but I don't know.
Yeah, it's no problem. Okay, I maybe I might.
Okay, thank you very much.
Thank you. Yeah, bye bye.
Have a good day. Thank you. Bye.
Yeah, bye bye.